Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the rectangle mania. This question gives you a list of Cartesian coordinates, meaning xy coordinates, and asks you to find the number of rectangles formed by those coordinates. It also gives us two specifications. The first one is that in order for a rectangle to actually be a rectangle, it has to have four corners present in the coordinates. And the second specification is that we are only concerned with rectangles whose sides are parallel to the x and y axes. In other words, if you look at the example in front of me, we would only care about rectangles that kind of look like this. We wouldn't care about rectangles that have diagonal sides like this. Now, this is a very difficult question because, first of all, it's the kind of question where the more inputs we have, for instance, if I were to add 10 coordinates to the 6 coordinates I have in front of me here in this example, the more impossible this question becomes to solve as a human being. Like if I were to add 10 coordinates to this plane here, it would be very, very difficult just as a human being to come up with the answer at a glance. And then the second thing that makes this question particularly hard, in my opinion, is that it's very different than most other coding interview questions because it involves sort of shapes and geometry by some definition of geometry. I mean, we're not asking anything too complicated, but we're dealing with rectangles on a plane with XY coordinates. This is not your typical coding interview question. And yet, it does lend itself very well to algorithms and data structures, and it is just in general a very, very good interview question. So with that said, let's actually dive into this question. In the example in front of me, we've got these 6 coordinates, and the answer is going to be 3. They form 3 rectangles because there's one right here, there's one right here, and then there's a bigger one that sort of captures the other 2. Now, the key to solving this question, and we're going to be covering 3 different solutions, so a lot of different ways of solving this question, but the key to solving this question is to realize that in order to have a rectangle, we need to have 4 corners. And if we use that as our sort of guiding principle, things start to become clearer. Things start to become easier. If we realize that we need 4 corners to have a rectangle, then what we can try to do is, instead of trying to arbitrarily find rectangles, we can say, let's find 4 corners. And if we find 4 corners, then we've found a rectangle. Okay, but then how do we find 4 corners? Do these corners need anything special? Do they have something special about them? Well, yes, as a matter of fact, they do. They do have certain properties that are going to help us find those corners. Because, for instance, if I draw on this plane here and I add a few points, if I add 1 point here, 1 point here, 1 point here, but then 1 point, let's say, here, you can immediately see this is not a rectangle, right? This is some sort of like weird shape that just isn't a rectangle. So what is the property, or what are the properties that 4 corners need to have in order to form a rectangle? Well, there's really only a couple of properties, which is that the 2 left-hand corners, meaning the 2 corners on the left-hand side of the rectangle, need to be directly on the same line. In other words, they need to have the same x-axis, or x-coordinate rather, but they need to have a different y-coordinate. The 2 right-hand corners, I guess let me erase this here, the 2 right-hand corners, let's say we have this as a rectangle, the 2 right-hand corners also need to be on the same x-coordinate, or on the same x line, right? And then the 2 top corners need to be on the same y-coordinate, and the 2 bottom corners need to be on the same y-coordinate. Another way of framing this is that if we find ourselves at any given corner, we know which points near us could be another corner of a rectangle that we might be in by just checking if these other points are on the same vertical or horizontal line as us. So for instance, if we look at this rectangle that I just drew, imagine we found ourselves here in the bottom left corner, and we wanted to sort of maybe traverse this particular rectangle, see if it existed in a clockwise pattern, meaning up, right, down, left. We would first check, basically, hey, do we have a point or multiple points, multiple coordinates, directly above us on the same, again, x coordinate? And here we happen to have one, right? We happen to have one right here. And so then at this point we can say, okay, well, now we know that we're dealing with the top left corner of a rectangle. Do we have points directly to the right of us? And here we do. We have this. And then do we have points directly below us? We do. We have this. And then we kind of find ourselves back at the beginning, right? So we kind of traversed this rectangle in a clockwise pattern like this and found ourselves dealing with the correct rectangle because we kind of made a full loop and found ourselves back at the origin. Whereas you can imagine, with the shape that I had drawn earlier, that looked kind of like this, we would start at the beginning here, we would go up, and here we would go to the right, and we would say, hey, there's no point there. There's just nothing here. So, okay, now how do we actually translate this into something that we can actually code out maybe into code? Well, let's treat, and let me erase this here, let's treat every single point or every single coordinate, pair of coordinates in our list, in our input list, as the potential lower left corner of a rectangle. So each of these 6 points in our example here, right, 1, 2, 3, 4, 5, 6, each of these 6 points we are going to treat as potential bottom left corners of a rectangle. And then the way that we're going to count the rectangles is by saying, well, if each of those is a valid bottom left corner of a rectangle, then we should be able to go directly up, find a top left corner, then for every potential top left corner, go to the right, find a top right corner, for every top right corner, go to the bottom, and so on and so forth. So what this is going to look like in practice is we're first going to say, let's grab all of our coordinates here, and for every coordinate, let's store the other coordinates or the other points that are directly above us, directly to the right, directly below us, and directly to the left. And this is going to help us find or easily do this clockwise traversal. So you might imagine that for this point here, the 0, 0 point, the origin, the point of the origin, we're going to say, hey, and I'll write it out, I guess, just for this example, but I probably won't do it for the others. This point here, we would say, hey, we know that directly up or directly above us, we've got 0, 1, which is this point. There's a 1 point directly above us. And we know that directly to the right of us, so I'll write right, there's 1, 0, and there's 2, 0. There are 2 points, right? 1, 2. Directly below us, there's nothing. And directly to the left of us, there's nothing. So now, when we start at this point, for instance, when we iterate through all the coordinates and we say, hey, I'm going to treat this as a lower left corner, and I'm going to do this sort of clockwise traversal, almost treating like these directions here, up, right, and so on and so forth, as a graph, and I'm going to follow that graph in a clockwise pattern. So I'm going to start by going up, then I'm going to go to the right from this point, and so on and so forth. This is going to allow me to do that. Okay? So now to kind of reiterate exactly what we're doing, for this particular solution, the first thing that we're going to do is we're going to iterate through all the points. And for every point, we're then going to iterate through all the other points and bucket them either as directly up, directly to the right, directly down, or directly to the left of us. Okay? So that way, at the end, once we'll have done this, we will know that directly above 0, 0, there's 0, 1. Directly to the right of 0, 0, there's 1, 0, 2, 0. And then there's nothing directly down and directly to the left. Then for 0, 1, there's nothing directly up. There are 2 points directly to the right, 1, 1, 2, 1. There's 1 point directly below, 0, 0. And there's nothing directly to the right. And we continue doing that for every single coordinate. And that way you can imagine, and maybe this will make more sense in the code, we'll have a hash table, basically, of every coordinate, or of every point, mapping to all of the points, again, in all 4 directions of that point. And this is going to take, obviously, O of n squared time, where n is the length of the coordinates, because we're going to iterate through all the coordinates once, and for each coordinate, we're going to iterate through all the other coordinates and bucket them in all these directions. So O of n squared time just to do that, and you can imagine that this will likely take O of n squared space, and I'll cover this a little bit later, but this will take O of n squared space because you could imagine that maybe every point is going to be on the exact same line. So it's possible that here, if you look at the bottom right here, I'm drawing another coordinate plane, we might have every single point on the x-axis like this. And if we have this, then for this point here, we would have to store every other point above it, meaning every other point in the list as points directly above it. Then for this one, the second one, we would have to store all of these. So for the first one, we stored all of these. For the second one, we stored all of this. For this one, we store all of these. For this one, we store all of these. And so as you can see, it's kind of, n minus 1 plus n minus 2 plus n minus 3. It's the equivalent of 2 nested for loops where one index is sort of in front of the other. So this is going to be O of n squared space as well. I guess here I kind of skipped the gun a little bit and went into the complexity analysis, but we'll recover that. And I think this is going to be the kind of question where the code kind of is a lot clearer than the conceptual overview. Hopefully the conceptual overview is just going to be useful here to understand how the algorithm works. But so once we have all of this, right, imagine, just picture in your head that we have this hash table where every coordinate maps to all of the coordinates directly above, directly to the right, directly down, directly to the left of them. Then we just do this clockwise pattern where we reiterate through all of the coordinates, but for each of them, treat it as a potential bottom left corner. And then in a sort of depth first search kind of way, so this is why it sort of resembles a graph, iterate in this clockwise pattern. You go through all of the coordinates directly above it. Then for all the coordinates directly above it, you go all the coordinates directly to the right, and so on and so forth. So let's actually walk through this example. I know I've been speaking a lot. Let's actually go through the example for here. We have this hash table, and now we start at the first coordinate. We're iterating through all of them, 0, 0. Okay, this is a bottom left corner, potentially. Go through all of the points above it. Do we have any points above it? Yes, we do. So go here above. We only have 1. For this point, go through all the points directly to the right. Do we have any? Yep, we have 2, but let's start with the first one. We're kind of doing a depth first search. So that's 1. And before we go into the second one, which is here, now at this one, this would be at this point a top right corner. So here now try going down. Do we have any points directly down? Yes, we do. We have 1. So go down. And then here, try to see if we can go directly left. Do we have any points directly to the left? Yes, we do. And this point happens to be back at the origin. So we've got 1 rectangle. Boom, we store 1 count of 1. Then we kind of go back here, we backtrack because this was a sort of depth first search, and here, up here at 0, 1, we had 2 points to the right of us. We had 1 here, but we had a second one. So now we have a second potential rectangle. Here, we are at a potential top right corner, so now go below. So we're going to go down here. And then here, we are at a bottom right corner. So see if we have any points to the left. We do have points to the left. That's going to be 1. Here, we're not at a corner yet. We are not at a corner yet here because our origin, remember, this is still from the very first point that we iterated through, which was this one. And so far, maybe I should write in brown the rectangles that we've counted. We have counted this as a rectangle. And now we are sort of going here, but this middle part, maybe I should do this in a different color. Let me erase this. No, redo. And now we are here. Purple, 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 right? And so at this point, here, we don't have a rectangle yet. We have like this broken thing here. This is not a rectangle. But then if we go one more point, because we're going again in a sort of depth first search kind of way and iterating through all of the points directly to our left, now we're back at the origin. And so now we've got a second rectangle. And now we're done. Now we've finished sort of iterating through the very first point, right? We've kind of exhausted all of the clockwise traversals. And now we can do the exact same thing from every other point. So again, we continue iterating through all the points and we treat them all as potential bottom left corners. So let's go with this one. I'll circle it maybe in white here, this one. Does this one have any points directly above it if it's a potential bottom left corner? No, it doesn't. So move along. Does this one have any points above it? No, it doesn't. Does this point have any points directly above it? No, it doesn't. What about this point? Yes, it does. So, okay, we're going to go up like this, right? We have one point directly above us. Okay, great. Now we're at a potential top left corner. Do we have any points to the right of us? No, we don't. So we're done. And we go to the final point, 1, 0, the final point that could be a potential bottom left corner. Does it have a point directly above it? Yes, it does. This one has a point directly to the right of it. Great. This one has a point directly to the right, below it. Great. And this one has 2 points directly to the left of it. This one creates a rectangle, the one that I'm putting in white here. And this one doesn't create anything. And the reason we know this one creates a rectangle is because we are back at our origin here. The origin, the original bottom left corner of this sort of clockwise pattern. And so that's it. Now we've counted a total of 3 rectangles. And now if we go back to the space and time complexity, like we said, the time complexity to kind of bucket all of the coordinates into these directions of directly above, directly to the right, and all that, that was going to be probably 2 for loops. So that's going to be O of n time. Right? Time equals, sorry, not O of n. What am I doing? O of n squared time. And then before we move on to the space, is there anything else? Well, what about the clockwise pattern? Well, the clockwise pattern, this one is a bit trickier to calculate because you might be like, well, okay, well, some of them are going to have points directly above. Some of them are going to have a ton of points to the right. How do we calculate this? Well, you can imagine that in the worst case, again, you would have like all the points on one line. Whoops, that did not look like one line, like this. And you'll have 1 point here, 1 point here, 1 point here, 1 point here. And so for all of the points, again, we'd iterate through all the points above, all the points above, all the points above. And so that's sort of like a double for loop. So again, that's going to be bounded by O of n squared. So the time complexity for this sort of clockwise pattern traversal thing is going to be at most O of n squared. Let me erase all of this junk. But so at most O of n squared. And then the space complexity, because we are storing all of these in these, all of the coordinates in these up-down kind of things, then we said the space complexity is going to be O of n squared as well. Where n, of course, is the length of the number of coordinates, the length of the list of coordinates. And I suppose we will also have, space complexity from the recursive calls if we use a depth first search kind of thing here. And we're probably going to do it with recursion. But again, you can imagine that the worst case would be when we've got all the points on one line. And that would, again, never exceed O of n squared. And probably, to be honest, it would never exceed O of n for the recursive calls. Yeah, because the recursive calls you will at most have n recursive calls. Um, Actually, not even. You will at most have 4 recursive calls because you are always doing 4 pattern. Like you are always at most you will be doing something like this and then backtracking back on your footing. So, as far as like recursion is concerned, you will have at most at most 4 recursive calls on the sort of function call stack at any given time. So overall, time and space complexity is O of n squared. Now, is there a way to optimize this? There is. There's first of all, there's certainly a way to make this cleaner in terms of code, but there's also a way to optimize this. And the reason I say cleaner in terms of code is because, as you'll soon see when we jump into the code, this is going to be a pretty meaty problem. There's going to be quite a lot of code to write. But here, what we can optimize on is this space complexity. Because we have to ask ourselves, do we actually need to store every coordinate for every other coordinate directly above, directly below, directly to the right, and so on? Because at the end, what constitutes a point being directly above or directly to the right or directly below or directly to the left? All we have to do is compare coordinates, right? So for instance, if I'm at this point, the 0, 0 at the origin, and I want to check all the points that are directly above us, we said, oh, we're going to store all these points in a hash table and we'll know them. We'll be able to access them easily from there. But another way to do it would just be to say, okay, when you're at this point, iterate through all the points above you, iterate through all the other coordinates in general, iterate through all the points. And if you find one point that's got a coordinate of the same x, but of a y that is higher, right? Because these points share the same x. They're both at x equals 0, but this one has a higher y. 1 is greater than 0. Then you know you're above. So basically, we can redo this exact algorithm with the same logic of clockwise pattern and, going up, then right, then bottom, then left. Except instead of storing all the points and positioning them as up, right, down, left for every other coordinate, we can just immediately start iterating through the coordinates and say, hey, for every whenever I'm at a coordinate, if I know that this is a potential bottom left and I want to go directly up, all I'm going to do is maybe store all of the coordinates indexed by x coordinate or by x value and iterate through all the coordinates that have an x equal to my x and a y greater to my y. And then when I find those points, and maybe now I'm at the top left corner, and I'm looking for points directly to the right, I'm going to say, oh, iterate through all of the coordinates that have the same y as me. So maybe I stored, again, all the coordinates indexed at their y value. And only pick the ones that have an x that is greater than me. Because here, again, if a point is directly to the right of us, we have the same y, 1, 1, but we have different x's, 0, 1. This x is greater than this x. So basically, for this solution, what we're going to do is instead of having a hash table of every single coordinate mapping to all of the other coordinates that are directly above, directly below, to the right, and to the left, we're just going to have a hash table of all of the we're going to have a hash table that has probably like 2 properties. One is going to be called maybe x, one is going to be called y. And in these 2 properties, we're just going to store all of the coordinates of a given x value, all of the coordinates of a given y value. That way we'll be able to easily access all of the coordinates of a given value. And when we access it, we'll just iterate through all of those coordinates and say, okay, well, what is the condition that needs to be met such that I find a point that's directly above or directly to the right or directly to below, we'll just do that computation in real time, which is a constant time operation, and we'll find the correct points, right? So you can imagine that for this example, we might have something like, this might be our hash table, right? Again, instead of having all the coordinates here mapping to points directly above, below, left, right of them, we'll have something like x, y, where x is something like 0. How many points have 0 as their x-axis? Well, there's 0, 0, and there's 0, 1, right? And then 1, how many points have 1 as their x-axis? Well, there's 1, 1, and there's 1, 0. And then, so on and so forth with 2, and same with y, right? So let me undo all of this just so that I don't mess myself up when I want to erase this afterwards. But so that's the second solution. And the second solution, again, maybe the code will be a lot more clear. But the second solution will be exactly the same sort of underlying algorithm of clockwise traversing points by treating them as a potential left corner and so on and so forth. But instead of storing all those points in that hash table, we will just store them by their x-axis, indexed at their x coordinate value and at their y coordinate value. And so that means that in terms of space complexity, we will only store every coordinate twice. Once indexed at its x value, once indexed at its y value. So that's going to be O of 2n for the space complexity. So I'm going to erase basically the square because we can lower it to O of 2n. Now, before we get into the code, I want to cover 1/3 solution of this problem, because as you'll see when we get into the code, these first two solutions, while we were able to do one little optimization in complexity, or in space complexity, they are, pun unintended, still very complex in terms of code. You'll see it's just a lot of lines of code. There's a lot of complexity in the clockwise traversing and all that. And we can eliminate that complexity. In other words, we can make this code very clean, just much prettier, much more readable, by just being a little bit clever. The little bit of cleverness here comes when we realize that we don't actually need to do this clockwise traversal of points or of corners. If we have, again, we take the same guiding principle of treating every coordinate as the potential bottom left corner, right? If we have a potential bottom left corner, then we know that if this is going to be a real rectangle, there must be a corresponding top right corner, meaning a corner opposite our corner. And what would be a valid top right corner? It would basically be any point in the upper right vicinity of our point. So for instance, for 0, 0, there are 2 points in the upper right vicinity of us, or upper right direction, 1, 1 and 2, 1. Right? So we have 2 potential rectangles because we have one bottom left corner here and 2 potential top right corners. But then if we treat now both of these potential top right corners as actually potential top right corners, then in order to validate them as rectangles, all we need to do now is find the top left and bottom right corners. And we can do that just because we have the bottom left and top right. Because look, if I draw here in the bottom right, I draw bottom left corner, bottom left, and then top right corner. If I have these 2 points, then I know that if I want a rectangle, I need to have a top left corner here. Maybe I should write this in green. I need to have a top left corner here and a bottom right corner here. And this is super easy. All that I need is to sort of take what would it be? The x coordinate, take the x coordinate of BL and the y coordinate of TR, right? So if this is x1, y1, and this is x2, y2, then this green one is x1, y2, and this one is x2, y1. And if I map or store every point in a hash table, literally just store the coordinates in a hash table for fast lookup, and probably we can stringify them or something, then I can say, hey, iterate through all the coordinates, treat every coordinate as a potential bottom left coordinate, then do a double for loop and iterate through all of the other coordinates again, and treat every coordinate that's in the upper right, and we can find if it's in the upper right easily in constant time with just a few, checks of values. And for every upper right point, that's going to be O of n squared, by the way, the double for loop, right? Iterate through every bottom left corner, and for every bottom left corner, iterate through all the other coordinates that are potential upper right ones. And here, just say, okay, see if x1, y2, top left corner is in our hash table, because we've dumped every coordinate in the hash table, and see if x2, y1, bottom right corner, is in the hash table. If they're both in the hash table, then count a rectangle. And we don't even need to like make sure that we don't double count or anything like that, because we're treating every point as a potential bottom left corner. If we treat every point as a potential bottom left corner, we will never double count a rectangle, right? We will have this as a rectangle, but then when we go and traverse through all these other points, these three other points, we would only have potential things like this, right? Potential things like this. We would never double count this rectangle. And so this is going to be, again, O of n squared time, because we're still going to be doing a double for loop. And it's going to be O of n space, because we need to store every point in a hash table. But it is going to be a lot cleaner. You'll see in the code, this is where we do have to jump into the code now, because you will just see that we're writing far fewer lines of code. It's much easier to read. It's literally just saying, like, for chord number 1, iterate through all the coordinates iterate through all the coordinates once, then iterate through all the coordinates a second time. If the second coordinate is not in the upper right of the first coordinate, just skip. And if it is, check if we have the top left and the bottom right, and we're done. Or you increment a rectangle, and then you're done once you finish iterating through all of them. So this one is going to be O of n squared O of n. So with that said, I hope that this video was informative, or that the conceptual overview was informative. Let's actually dive into the code to see what it looks like. All right, so we've got our rectangle mania function defined. It takes in a list of coordinates. And for this first solution, the first of 3, we are going to bucket for every single coordinate all of the other coordinates that are directly above it, directly to the right of it, directly below it, directly to the left of it. This is going to be the longest solution, the most tedious to code out, but let's jump into it. The first thing that we do is we declare this chords table. This is going to be the table or the hash table that stores exactly what I just said. And we'll abstract the logic for generating this table out into another method. So get chords table. This is going to make our code at least easy to follow, even though it's very long. And here I do want to point out that for this method, this is the kind of method where I would advise asking your interviewer in an interview if you actually need to write this method out, because it's kind of easy to write out, just long. And I think that there's more interesting code further down in this algorithm when you do the actual sort of clockwise pattern traversal. So always worth asking your interviewer. It might save you some time. Let's actually code it out though. So def get chords table. It takes in a list of chords. And of course, it declares the chords table that we'll return. This is a hash table, so a dictionary in Python. And then we start a double for loop. So for chord 1 in chords. And here we'll do for chord 2 in chords. So we're iterating through all the chords, and we're saying, hey, for every single coordinate, grab all of the other coordinates and bucket them either directly above, directly to the right, etc. So here we might actually declare an object that we'll call something like chord 1 directions. And this will be also, a hash table. And it'll look maybe something like, it'll have all the directions. So maybe we'll store variables for the directions as well. That way we don't have to sort of hard code them. So we'll do something like up and this will be an array of coordinates. Right, this will also be an array of coordinates. Down, this will be an array of coordinates. And finally, left, this will also be an array of coordinates. And so here you can imagine that we might hard code them at the very bottom, something like up equals up, literally right equals right, down equals down, and left equals left. So once we have these directions, we can say for chord 2 in chords, and we can say, let's actually grab the direction of the coordinate number 2 with respect to coordinate number 1. Is it directly above? Is it directly to the right, etc.? So we'll say chord 2 direction equals, and we'll maybe create another method here, get chord direction, passing in chord 1 and chord 2, and we'll write this out in a second. And here, we definitely have to do a check where we have to say, hey, is this second coordinate directly above, to the right, down, or left? Because if it's like diagonally positioned, then we don't want it, right? For this algorithm, we only care about things that are directly in one direction. So we can say something like if, and here I guess we don't need parentheses, if chord 2 direction in chord 1 directions, then chord 1 directions of chord 2 direction, because you can imagine that this will return like up, right, down, or left, is going to be equal to, or rather, this is an array, so we're going to append the second coordinate, right? Because we're saying if our coordinate number 2, right, is, let's say, directly above our coordinate number 1, so coordinate number 2 direction is in chord 1 directions, so one of these 4 values, then grab the array that this value maps to and append that coordinate. And then we want to store these chord 1 directions in our hash table, and we want like chord 1 to map to these chord 1 directions. In Python, I think that you can index, like you can have a hash table or a dictionary have a tuple or an array as a property, I think. But we're just going to stringify our coordinate. The prompt tells us the coordinates are only going to be, within a radius of like 100 or 1,000 from the origin, so stringifying should be fine. So we're going to do something like chord 1 string equals chord 2 string of chord 1, and then we'll do chords table of chord 1 string equals chord 1 directions, right? And then finally, we return our chords table. So if we actually write some of these methods out, let's define the chord to string really quickly. This should be a very simple method that takes in just a chord, and it'll return, we can say like x1, x2, or x1, y2 rather, or x1, y1 equals chord. And then we can do something like return string of x1 plus, hyphen plus string of y1. I guess we can just call these x and y. We don't need to call them x1 and y1. And then the next thing that we are going to do is going to be to write out this get chord direction method. So this is going to be get chord direction. It's going to take in, I guess we said 2 coordinates, right? Chord 1, chord 2. And this is just going to be a kind of an annoying function where we just have to do a bunch of if-else statements. So to make it clean, we'll call the coordinates, x1, y1. So x1, y1 equals chord 1. Nope, not chord 1. x2, y2 equals chord 2. If the two y's are equal, if y2 is equal to y1, and if x2 is greater than x1, then we know that we are on the same y coordinate, but we are on we're farther to the right, right? So return our right variable. If, or elif, x2 is smaller than x1, return left, and then we can do checks for, elif x2 equals x1, if y2 greater than y1, then we are above, right? Return up. Elif y2 greater than y1, return down. And here you might notice that I'm doing elif instead of else, because if we ever deal with, like if we're double counting, if we're at the same coordinate, like a coordinate that's on top of us, we don't want to, we don't need to visit that. So here we can just kind of return maybe, I don't know, the empty string or something. And this is going to be the case where this if condition here, if chord 2 direction and chord 1 directions might not actually get hit because we have an empty string if we're not directly above or directly to the right, and so on. So then we are done with getting the chords table. So now we can move on to the more exciting part of the algorithm, which is going to be actually counting the rectangles. And so here, I guess we can do just return get rectangle count, and we're going to pass in our coordinates as well as our chords table. And this get rectangle count method is going to be the interesting one. Let's put it down here. Def get rectangle count. We said chords table. And let me give myself some space here. So this is where things get interesting, right? So how do we count the rectangles? We said that we wanted to iterate through all of the coordinates, treating everyone as a potential bottom left corner, right? So we're going to say our rectangle count to start is equal to 0. And we iterate through all the coordinates, for chord and chords. And here we do this sort of depth first search clockwise pattern traversal thing. So we can increment our rectangle count. We'll have a recursive function that sort of returns the rectangle count for a given coordinate. So basically it's going to say like, hey, if this coordinate is a valid bottom left corner, get the rectangle count of all the rectangles with that as a bottom left corner. So rectangle count plus equal to clockwise count rectangles. This is going to be our really main meaty method. And we'll give it parameters in a second. And then finally, we can return the rectangle count. And here we would be done. What would clockwise rectangles need to take? It would need to take the coordinate that we're at, of course. It would need to take our chords table, since we're going to need that. It would need to take the direction that we're currently going in, which I guess to start, if this is a bottom left corner, then we would be going up. And it needs to take the original bottom left corner. Because remember, we're going to have to close this method out at one point where we find a rectangle, or when we find a rectangle. So we're going to pass in our coordinate, like this coordinate, the bottom left corner, here it is. And so now we can define clockwise count rectangles, takes in chords table, direction, and we're going to call this the origin, I suppose. And what are we going to need to do here? We need to say, depending on the direction that we're going in, do something, right? So if our direction is equal to the left, if we're going to the left, then we're trying to find if we've found a rectangle. We'll handle that in a second. But otherwise, if we're not going to the left, then we're either going above, to the right, and below. And so here what we can do is we can say, okay, let's actually count our rectangle count. Again, we'll have to initialize that to 0 here. And we can say for whatever the next coordinate is, what's the next coordinate? Here, it's whatever coordinates are in our direction, right? If we're going up, then we have to iterate through all the coordinates above us. If we're going to the right, then we have to iterate through all the coordinates to the right of us, and so on and so forth. So we need to get the next direction. We need to know what points we're going to be looking at. So we can say next direction equals get next clockwise direction. And this should be, again, kind of a tedious method that I would ask your interviewer if we need, but let's just code it out here. It's going to take in a direction, and it's going to say, hey, if direction is equal to up, return right, right? If direction is equal to right, then return down. If direction is equal to down, then return left. What am I doing here? And I suppose we don't even need, like, if our direction is going left, because if our direction is going left, we're going to handle that here. So I'm just going to end here and maybe just, like, return an empty string again or something. But so now that we have the next direction, we can say for next chord in our chords table. And so here we need to access all of the coordinates that are in our direction. And then we're going to sort of clockwise traverse all of the coordinates in the next direction that we just calculated. So if we want to access stuff in the chords table, we're going to need to know the string value, because remember the chords table here it maps string representations of coordinates to all of these directions. So I'll write up here, what am I going to write? I'm going to write chord string equals chord to string of chord. And we'll say, let's see, the next chord, we're looking at the chords table of our chord string in our direction, right? In our direction, like we have our table, we are at this coordinate that has this as a chord string, and we're going up right now, for instance. So we're looking at all the points that are up. These are all the next coordinates that we have to explore. And then for all of these, rectangle count plus equal to, we call the method again, clockwise count rectangles. We pass in the next coordinate. We pass in the same chords table. We pass in the next direction, because now, look, if we're going up and we're taking a coordinate that's directly above us, right? Taking a coordinate that's directly above us, we want to now go to the right, which is why we calculated this next direction here. If we were going to the right, we would be looking at all of the next coordinates that are to the right of us, and then we would be getting all of these coordinates and calling clockwise count rectangles going down, because the next direction would be going down. And here we make sure to pass the origin. And I think this is it here. And then we can just say return rectangle count once we've counted all the rectangles that are sort of, eventually go back to the origin, meaning they have a lower left corner coordinate. And here we do need to handle the base case, which is when the direction is left. When the direction is left, what are we looking for? Well, we need to make sure basically that in all the coordinates directly to our left, there's an origin, right? We find our original point. So basically we can say like rectangle found, I guess, this is going to be a Boolean, is equal to origin in chords table chord string to the left. And then we can say like maybe a ternary, return 1 if rectangle found, else 0. And boom. Now we've got our method, right? So let's delete all of this stuff and let's try to recap everything that we've done here. Right? So we have our rectangle mania function. We start by declaring this chords table. To get this chords table, we do a double for loop through all the coordinates, and we say, hey, what's the direction of this coordinate with respect to the first one? This does a bunch of checks to just see like, hey, based on the x, y values, is it to the right, is it to the bottom, or is it just like diagonally positioned, in which case we don't care. And then if it is directly to the right or directly above or whatever, we store it in these chord directions. And we do this for every single coordinate and store everything in the hash table. This is going to be n squared space, because you can imagine, again, we gave the example of imagine they're all in a straight line. So we're going to have just like, the first coordinate has all the other coordinates above it. The second coordinate has all the coordinates except the first one above it, and so on and so forth. And then we get the rectangle count. For the rectangle count, what did we do? We said, okay, iterate through all the coordinates, treat every single one as a potential bottom left corner. Then for all of those, clockwise count the rectangles, pass in the direction. We start by going up, pass in the origin, which is the current coordinate. And when we clockwise count, make sure to create a string so that we can access stuff in the hash table. If we're going to the left, we're at the final sort of sector. A rectangle will be found if our origin is in our chords table for the current coordinate to the left, right? If our origin is to the left of the current coordinate, basically, and return 1 if that's the case. Otherwise, return 0. That's our base case. And if we're not going to the left, if we're going up or down or to the right, then, calculate the next direction that we need to go in, go through every coordinate that's in our current direction, meaning maybe currently above or currently to the right, and for all of those, clockwise count the rectangles with the next direction, right? And here we know how to get the next clockwise direction by just doing a few checks. And this method is pretty easy here, and then we've hard-coded some values here. And so this method, like we said, is gonna run in O of n squared time O of n squared space. Again, I'll go through this one last time before we get into the other code or the other two solutions. This method here is what takes n squared space and n squared time. And this method, the clockwise count rectangles, will take at most n squared time. Again, the best example to think of that is that if everything is in a vertical line or everything is in a horizontal line, the vertical line is better because you start by going up. Then it almost mimics 2 for loops where the j index is moving ahead of the I index, right? You're doing first counting n-1 rectangles or n-1 coordinates above, then n-2 coordinates above, then n-3, and so on and so forth. And as far as recursive calls on the call stack, you'll only have at most 4 because there are only 4 corners, right? Up, right, down, left, recursive call. Okay. And everything else you can see are constant time operations. Okay, so that's solution number 1. Let's actually comment all of this out and let's go through the second solution. We are getting closer and closer to being done with this problem, but it is very important to see these solutions because they do give a good insight into how, the different ways of solving this question. There is no sort of better way. I suppose this first way is worse in terms of space complexity and also just complex code, but overall they're all decent. So Rectangle Mania, right? It takes in Rectangle Mania. It takes in a list of coordinates, and what do we do here for the second solution? Let's see. This one is the same as the first one, except instead of storing all the values in a hash table with directions, we are indexing every value at its x coordinate and at its y coordinate. And then we are going to find values that are above or to the right by just iterating through those x coordinates or to their y coordinates. Okay, so hopefully this will make more sense in the code. But this is very similar to, the main method is very similar. So we're actually just going to copy paste this and we'll comment the code out. Chords table, get chords table, and return the rectangle count. The get chords table function is going to be different. This one is going to say, okay, our chords table, instead of having all of the coordinates, is going to have, as properties, it's going to have x and y values, right? So it's going to be x and y values, and x is going to map to an object, and y is going to map to an object or a hash table. And in here, we're going to have stuff like 1, -1, 3, and all of these are going to map to all of the coordinates who have an x value of 1, of -1, of 3, and same for x, or same for y, sorry. So we'll say for chord in chords, xy equals chord. And here we do have to check at first if we actually have an xy value in these two hash tables. So that's kind of tedious. Again, here I would tell your interviewer, do you want me to write this out or do you not really care if I write this out? So here it's going to be if x not in chords table of x, then chords table of x at x. This is a bit complicated here, or annoying, is equal to empty array. And then we can do chords table of x dot append, because this is an array coordinate, right? And then here we can just copy paste this, and we can say if y not in chords table y, and chords table y at index y equals an empty array, and we append to this, we append the coordinate, right? And then we return the chords table, and again, now we have a table that says, hey, we have two properties, the x's and the y's. In the x's, we have all of the different x values that our coordinates have, and for each of those values, we have the list of coordinates with that x value. And same thing for y. And this is going to be O of n time to just create this table, and it's going to be O of n space, because we're just doing one for loop, right? And then just constant time operations. And it's going to be O of n space because we just have the coordinates multiplied by 2, right? In this hash table here, we're going to have all the coordinates, and in this one, we're going to have all the coordinates. So O of 2n space, O of n space. Okay, now we do the return rectangle count, or get rectangle count. So this one is going to look sort of similar to the other one, get rectangle count. It's going to take in chords and a chords table. And it is going to be rectangle count equals 0, right? We initialize it for chord in chords. And here we can say, let's get the origin again, or maybe we can call this, I don't know, the lower left y is going to be equal to chord 1. And then we do the same thing where here we return rectangle count. And here, I guess, we increment rectangle count. So rectangle count plus or equal to our recursive method, the clockwise count rectangles, which takes in a coordinate, takes in our chords table. It takes in the direction that we're going in. We're still doing the same logic, right, of doing up, right, left, down. We're just finding the up values and the right values a bit differently. But so here it'll start with up, and here it'll be lower left y. We could have named this the origin again. It doesn't really matter. Okay, finally, our, I guess, by the way, up, we need these values again. So we're going to copy them and put them here and comment them out. We might not need left, actually. Do we need left here? Because we can say, at the end, we can say, to be honest, did we even need it? Maybe we didn't even need left in the first solution. So we can just say at the end, like, if we find ourselves in the lower left y, right? This is why here I only need the y and I don't need the actual coordinate. Let's see if we cut it out and it works. Okay, so let's go with def clockwise count rectangles, and here this is going to take, what is this going to take? Chord 1. It's going to take chords table. It's going to take the direction, and it's going to take the lower left y. We get x1, y1 from the first coordinate, and we say if we are going down, if we are going up, let's see. What do we need in terms of, what is our base case? Our base case, I think we don't need our base case to be left. Our base case can just be down. Our base case can say if direction is equal to down, then we know we just need to find a point that has the same y value as our lower left y. And we will be on that same sort of like the horizontal line, and we will have a rectangle. So we'll say if direction is going down, then the relevant chords that we need to look at are going to be equal to chords table of x at index x1, because we're looking for all the values of the same x, but of a different y1, where y1 is equal to lower left y. So we can do for chord 2 in relevant chords, lower right y is going to be equal to chord 2 of 1. And we can say if lower right y is equal to lower left y, return 1. And then if we never find anything in this for loop, then return 0. So that is our base case, right? Again, here, the thing we're doing is we're saying, hey, if we're going down, then we want to look at all the coordinates that have the same value in x as our current coordinate. So we know that the bottom right corner, the lower right corner, has the same x value as the top right corner, and that's where we're at if we're going down. And then if we see that the lower right y of any of these coordinates is the same as our coordinate, then it has the same lower right y and the same x. It has the same lower right y as lower left y and the same x as the top corner, top right corner. So we found one. Otherwise, we return 1. And then here we're going to have a big else statement. So here this is going to be something along the lines of we have to count the rectangles. It's sort of like the previous method where you kept track of the rectangles. So let's see. Else rectangle count equals 0. And here we have to handle things. We have to handle the direction that's going up or right. So I guess we'll do if direction equals up, then relevant chords is going to be, we're also looking here at the same thing here, right? Because we are looking at values that have the same x value. Whoops, I did not mean to do that. Let me escape this. Relevant chords equals this. And for chord 2 in relevant chords, we can say y2, we're looking at y2 here, is going to be equal to chord 2 at index 1, right? And we can say is above, let's be overly explicit about this, is above equals y2 greater than y1. If is above, this is basically what we're doing here. Instead of saying we're going to iterate through all the coordinates that we know are directly above us, we're going to check if it's above, right? If is above, then rectangle count is going to be plus equal to clockwise count rectangles, chord 2, chords table, going to the right now, because after we go up, we go to the right, and we pass the same lower left y. Let me give myself a bit of space here again. And I don't think we need an else for the if it's not above. If it's not above, then we just skip it. And here we can say, oh, I did direction. Here we can say elif direction is equal to right. If the direction is equal to the right, then the relevant chords is going to be equal to the same thing except with y's now. Now we're caring about y's, so we'll do y, and we are looking at what? We are looking at y1. If we're going to the right, the points to the right are going to be on the same y, and we'll do for chord 2 in relevant chords. X2 equals chord 2. It's the same thing, except we're just like using x's now. Chord 2 of 1. We can say is exactly to the right equals x2 greater than x1. If is right, and we'll just copy paste this line here, except here we're going now down. Lower left y, and then finally here in this else statement, we are going to say return rectangle count. Okay. And I don't think we used the left value here, so we probably don't need this left value hard-coded. So let's go through this method one more time before we get into the final one, which will be a lot quicker and just a lot nicer to read. But we have this chords table. The chord table just says, hey, for all the coordinates, dump them in this .x property at the x coordinate that they have, and same for the y's. This is just O of n time. Because we are storing, we're doing one for loop and just constant time operations, and O of n space because we're storing every coordinate twice. Then we do the rectangle count. We're doing the exact same thing as the first method, to be honest, except we're only storing the lower left y instead of the full coordinate of the bottom left corner. And to be honest, I think we could have done this for the first solution as well. It wouldn't really have optimized anything, but I think we could have done it. I guess it would have optimized things in practice, but not in terms of complexity analysis. And then we have this clockwise count rectangles, and it's doing the exact same logic as in the first question. except it is finding the coordinates that are immediately or directly above or directly below and so on and so forth. Like here, we're saying, hey, if we're going up and we know that the relevant coordinates to look at that could be exactly above us are the ones that have the same x-axis as our current coordinate, and the ones that are above are the ones that have a y-axis or y value, that's greater than our y value. And if we found those, then we add a rectangle count of going to the right of that coordinate. And then same thing when we're going to the right, we look at all the values that are going to be directly to the right, meaning they have the same y value, and if their x value is greater than they are to the right, and then we go down. And then if we're going down, we are at the base case. When we're going down, we're looking for points that are on the same x-axis, and if we find a point with the same x-axis that's got the same not x-axis, x value, that's got the same y value as our lower left y, then we found a rectangle and we return 1. So that's this method. This method is going to run in the same time complexity, O of n squared time, because again, even though this is O of n, the clockwise count rectangle is going to be at most O of n squared, and then, or in the worst O of n squared, and then it's going to be O of n space because we are not storing all of these like directions like in here that could be in the worst case O of n squared space. All right, we're almost done. We're going to do this one more time. Re-comment this out. We're going to go with our third solution. And so this one is going to be, I guess we're going to do the same thing again. I can just copy paste the Rectangle Mania main function. So let me copy paste that. Okay, so here we get a chords table, but our chords table is going to be way simpler. And this is really where, I would argue the reason this solution is actually much better than the others, even though it has the same time and space complexity as the second solution, is that it's just so much cleaner in code, so much easier to understand, right? We do def get chords table, taking it in chords. This is going to be as simple as our chords table is an object, right, or a dictionary. For chord in chords, just create a chord string. So we'll copy our chord to string method coordinate, function, and we'll copy it from here. And again, in Python, I do believe that we don't need this. I think we can just store a tuple or a list as an index in a dictionary. I forget. But in a lot of languages, you can't really do that. So we're just going to stringify it. And we stringify it, and then we just say chords table of chord string is equal to true. You could also create a set here instead of a hash table if you prefer that in your language. I just kind of like using the very, very fundamental data structures like a hash table. And then we return the chords table. So this is what? O of n time, easy peasy. And then get rectangle count. This is going to be way, way simpler. Chords table, def get rectangle count. This is going to be way simpler. It takes in chords and a chords table, and it says, hey, let's keep track of the rectangle count, but we're not going to do any recursive stuff. We're just going to say for chord 1 in chords. And here, to be honest, let's actually destructure this into x1, y1 immediately. For x2, y2 in chords. So we're doing a double for loop, hence the O of n squared time. Now we check, is this second coordinate in the upper right corner or in the upper right direction of the first coordinate? Remember, the solution says, do we have a potential matching or corresponding top right corner, right? So we can say, if not is in upper right, and we'll declare an is an upper right function. We'll do it in a second. Continue. If we are in the upper right, maybe let me just declare this method already. Def is an upper right. This is going to take what? It's going to take chord 1, chord 2, x1, y1 equals chord 1, x2, y2 equals chord 2. And what determines if chord 2 is in the upper right direction of chord 1, x2 has to be greater than x1, and y2 has to be greater than y1. Yeah, this is correct. And so then we can say for x1, if not is in upper right, so I guess we have to pass in the two coordinates, so chord 1, and we have these values. So we'll just recreate the coordinates here. We'll say x1, y1, x2, y2, like this. If it's not in the upper right corner, continue. If it is in the upper right corner, we're iterating through all the coordinates, we're treating them as lower left corners, and for every other coordinate, if it is in the upper right corner, so it could be an upper right corner or top right corner, then we want to see if there are corresponding coordinates directly above our lower left corner and directly to the left of our upper right corner. So we can call this the upper chord, right? And we can directly stringify it because we're going to look it up in the hash table. Upper chord string is going to be chord to string. And what is the coordinate? The coordinate that would be in the upper left corner would be x1, y2. We would have the x coordinate or x value of the bottom left corner, but it would have the y value of the top right corner, right? And then similarly, the right chord string is going to be the exact same thing, except this one is going to be x2, y1, right? It has to be on the x coordinate of the top right corner, but the y coordinate of the bottom left corner. And then we can do a simple check where we just say if upper chord string is in our chords table and right chord string is in our chords table, then rectangle count plus equal to 1, and we return rectangle count, and we are done. We are finally done. And here we don't need anything else, so I'm going to just delete all this extra space for perfectionism. And there you have it. So this, again, this get chords table is just an o-then operation, and get rectangle count is just a double for loop that then does a very simple constant time couple of checks. These checks are just saying like, hey, we know where the bottom left corner is. We know where the top right corner is. So now we can guess where the corresponding top left and bottom right corner would have to be. Let's just find them and see if they're stored in our chords table, which we can look up in constant time because it's a hash table. And the is in upper right is also a constant time operation. And so that's that. So this method is going to be the same as this, o-then squared time, o-then space, because we do have to store every coordinate in the hash table, but it's just a lot simpler. And I would argue that if you give this to someone to read, they will directly understand what's happening, whereas the other two solutions would take a little bit more time. With that said, I really hope that this video was informative. I know that this is a very long one. This might have the record for the longest video on AlgoExpert. This is a very, very good question. It's a very difficult one. Make sure that you understand it. If you are ever faced with similar questions, you will be very well equipped if you understand this one. And I will see you in the next video.